So in this video, we are going to learn about exponential smoothing with a linear trend, sometimes also known as Holt's method. This is another time series forecasting method, and this is an appropriate method if your time series data has two systematic components. It has a level and a trend. As a reminder, all data points have a level because you can take an average as long as there's, at least one data point, you'll always have a level. But as you can see in this simple example of the blue line, this one looks like it has also an upward trend. So there's a level and a trend. And so if your data in the past has these two systematic components, Holt's method, or again, exponential smoothing with a trend, would be an appropriate forecasting method. So once we've picked an appropriate forecasting method, we now need to actually create the forecast. And creating the forecast for this method basically means setting two what's called smoothing constants. So we'll now have alpha and we will have beta. And so alpha will adjust the amount of weight we put on the closest versus the further away in terms of the level or the intercept value. And beta will do that same thing, but for the trend. So we care about the delta, the change between one or the other. And they are both exponential smoothing weights, but they're doing different things on different aspects of the time series. And so, kind of high level, and I'll show the math in the next slides, this is an approach that's sometimes called additive because we're adding the level plus the trend component in a kind of weighted way. All right, so how would we actually go about doing that? In the first step, we would need to compute the smooth component, the level component. So this is L of t. This equation looks similar to what we saw in the simple exponential smoothing, but it's not exactly the same. So I want to emphasize this equation is not exactly the same. One thing to note is we have a t trend component, but we have this kind of alpha times my actual demand, d of t, and then 1 minus alpha of kind of the forecast aspect of this. So that would give us the smooth component. And then we also need an estimate for our trend component. So here we're going to call that t of t. So the trend component in t of t plus 1 has this beta and then 1 minus beta aspect of it. And you can think about what is going on in this first term. Well, you're basically looking kind of high level and saying, what happened here minus the one before it? So you could think about this a little bit like a delta. How much did it change? Did it go up or did it go down? We're not using the actual observed data. Instead, we're using the level component, but that's what's kind of going on there. Did my data go up or down most recently? And then we have kind of the forecasted part captured inside this trend component. And one thing to note, to be able to get t of t, you need L of t. And so you do need to do these kind of sequentially. The beauty of doing this in R is that it'll take care of that. But if you wanted to do this by hand, you need L of t before you can get t of t. And now we would actually calculate the forecast. So we'd calculate the forecast for n periods out. And we oftentimes do what's called a one step ahead forecast. We do that because we need to forecast the past in order to set what should alpha and beta be. And we'll talk more about that in a couple of slides. So if n is 1, the one step ahead, you can notice here that you have L of t plus t of t. But as you get further out, because systematically there's a trend in our data set, as you get further out, you expect that trend, if t of t is positive, then it should be bigger as you go further. If t of t is negative, as I go further out, it should go down. And that's what's happening with this part of the equation. All right, so one aspect of this problem is in order to get L of t plus 1, I need L of t. Similar to get t of t plus 1, I need t of t. So in other words, I need to initialize this model. And so this requires an initialization. So you could think about, I need to start somewhere. I need an initialization for L of 0 and t of 0. And that is, again, because these equations, to get L of t plus 1, I need an L of t. And to get t of t plus 1, I need a t of t, right? And so there are many ways you can think about initializing. The book recommends to take your historical data and then run a linear regression model. And then once you have that simple regression model, this is basically equation of a line. You would say the rise over run, the A, the slope would be my estimate for the T of 0. And then the intercept would be my estimate for L of 0. So that's a way to estimate L of 0 and T of 0. Holt-Winter's function in R, which we're going to do, uses a decomposition approach. So kind of similar to this regression approach. And if you're interested, you can look at the question mark Holt-Winters, and I'll tell you about all the details. But the key thing is you do need to initialize it. These are ways to potentially initialize. All right, so let's actually just apply this. So one of the things I want to emphasize is in order to apply a forecast, you need historical data because this is a time series. You also need values for alpha and beta. For this example, I'm going to set alpha of 0.2 and beta of 0.4. The logical next question is how do you set those? We'll talk about those in the slides after the example. But to remember to create a forecast, we have to figure out what those input parameters should be. I'm going to use alpha 0.2 and beta 0.4. And let's assume we maybe set them using minimizing error rate, but that is something you need to do. So we figured that out, maybe using past data. And now let's use it to forecast. So first we need to start off, we want to calculate L of 0 and T of 0, and we don't have, L of -1, right? So we just need to initialize. And so I'm going to run the simple linear regression. And if you do that on the actual demand that I have, so I have 8 pieces of data, if you run that, you get a linear regression of 11.32 plus 2.2 T. And so that's what I'm going to use as my L of 0 and T of 0. Again, there are other ways you can initialize, but I'm going to use that. All right, so now that we have L of 0 and T of 0, we can actually calculate L of 1, right? So we can calculate the level estimate for month 1 using this equation here. Again, this equation uses alpha. And if you think about alpha, what is it doing? Is it matters how much weight do I have? How steep is my exponential smoothing curve? And so I'm going to just plug in. I have the values of alpha 0.2, D of 1, which would be 12. So the actual observation in month 1 was 12. And then what am I doing here? I'm adding my kind of previous 11.3 and 2.2. You could think about that as kind of the forecast, right? And so that gives me 13.2. That's the value for L of 1. Now that we have L of 1, we can get T of 1. So here we're now using beta, and we're getting an estimate for the trend. And so beta here, we're going to use 0.4. And so what is happening, we're basically taking L of 1 minus L of 0. So we're basically taking this value here, and we're saying, does it go up or down? And so we are getting bigger, so the trend is a positive number. And so you could think about this as the most recent value. And then in the past, we had 2.2, right? And so again, this is exponentially smooth in terms of a beta, but how much weight do I put on them versus another is 0.4. And so you get 2.08 for T of 1. All right, now we finally can forecast something, okay? And so as a reminder, the forecast equation for exponential smoothing with a trend is L of T plus N times T of T. And so if we want to calculate the 1 step ahead forecast for month 1, N would be 1. And so we would plug in whatever we got for L of 0 plus 1 times T of 0. And that would give me 13.5. And so you can see we're, kind of 1 below here. And we could keep doing that. Okay, so then we could go to L of 2, T of 2, F of 2, and we keep doing that until we run out of our demand, right? So one thing to emphasize is we can't calculate L and T unless we have actually observed demand. And so once we hit that point, we can forecast out into the future forever by just changing this N value. And we'll kind of use an example of that later in this presentation, but keep that in mind, how that would work. So hopefully that makes sense. So you've kind of by hand calculated the exponential smoothing with a trend. And so if you did this, kept doing this, the blue, dark blue is my actual demand. This like teal color then is my forecast. And you can see it's forecasting. It's kind of following that trend, which is good because my historical data has that, which is positive. And so you could say, okay, we just did that example with alpha 0.2 and beta 0.4. And so the next question is, how should we set alpha and beta? And so if I change alpha and beta, what happens? Well, basically this teal colored line changes, right? So these equations I just went over will change if I have different alpha and betas. And so the key concept to like creating the forecast is to figure out what value should alpha and beta be. And so how do we do this? We usually try to minimize the difference between these two lines, right? And we find some sort of error measure. And so if we use MSE, mean squared error, I would take in period 2, what's the difference between the dark blue and the teal, square it, plus what's in period 3, the difference, and so forth. And I want to minimize that difference, right? And so by changing alpha and beta, it changes the teal and it changes how much difference there is in between those. And we should pick alpha and beta that minimizes those errors. Okay? And so just to kind of break that down, we can do that kind of like discreetly, kind of trial and error. I don't recommend this as an approach. I recommend using R and does an optimization, but I think it's useful to think about what's going on. So you could think about setting explicitly for that same data set, I'm going to try alpha 0.1 and beta 0.1. By doing that, I would get a different forecast, right? One step ahead forecast. And then based on that, I could calculate the mean absolute deviation, MSE or bias. These are all just measures of forecast error. And then I could say, okay, what if I change alpha 0.1, beta 0.2? And then I change that, calculate these measures, and just keep doing that. And you can think about, you're doing both of these simultaneously for exponential smoothing with a trend, right? And so you could do that, and then you could say, okay, what should alpha and beta be? And so here, if I look through, I could find the minimum MAD and MSE. It occurs when alpha is 0.3 and beta is 0.5. And therefore, it'd say, okay, I should set alpha as 0.3, beta as 0.5. One thing to note, this is for specific observed data. As a reminder, you can only calculate forecasting error if you actually have something you've observed. So that's one thing. The second thing is this is the power of the R line of code. In one line of code, it basically solves in a nonlinear optimization model setting alpha and beta simultaneously that minimizes sum of squared errors, SSE, which would be equivalent to minimizing MSE. And so the beauty is behind the scenes, that's what's happening in Holt's winter. But I wanted to give you a little bit of insight by kind of breaking this out. Awesome. So hopefully you understand kind of theoretically what's going on. In the next video, we will actually implement this in R. But to get hopefully an understanding, I want you to test your knowledge. And so my question for you here is, the last period you have demand data for is April. So you have observed April, you have D of April, you have a value for that. But I don't have D of May, I don't have D of June, I don't have anything, it's just April, okay? So given that, what equation would you use to estimate an exponential smoothing with a trend forecast for June? Would you use A, the L of t plus 1 equation, B, T of t plus 1 equation, or C, F of t plus n equation? Pause, think about this. Hopefully you said C, okay? C is the correct answer because if I wanted to calculate the L of t plus 1, I need D of t plus 1. So if I want to calculate L of June, I need D of June. I don't have that, okay? So I couldn't use this equation. Similar for T of t. If I wanted T of June, I need L of June, and I just said I didn't have L of June because I don't have D of June, right? So I am not able to calculate a new L estimate nor a new trend estimate until I have observed data. And so what I would use is I would use this equation. And the last L and T that I would be able to calculate would be in April. And so what I would use is I would set N of 2 because April plus 2 is June. And so I would use L of April plus 2 times T of April, okay? And so key thing here is this equation is the forecast into the future. And because our historical data has a trend, we want to capture that trend into the future. Hence that the forecasts that go on into the future change with N, okay? So that brings me to my next kind of thought question is, again, the last period you have demand data for is April. So the last observed data is D of April. You used an exponential smoothing with a trend forecast, and you obtained the trend estimate in April for some value T of April, right? And that was positive, okay? It was greater than 0. So my question to you is, true or false? The forecast for May will equal the forecast for June. So the correct answer here is false. So in exponential smoothing with a trend, into the future is not the same as we saw in simple exponential smoothing. That's because of this equation of the N. So in May, we still, you can see here, use L of April and T of April. Those we use for both anything into the future. However, the forecast changes because, again, we said in the past, our data had a trend. So in the future, our data should have a trend. And so these are similar forecasts, but they're not exactly the same. And you can note we are one step, we account for one step of that trend in May because we're one step away. We count for two aspects of that trend in June because we're 2 steps away from our most recent data. So hopefully that makes sense. And to note that when you see this in R, when we implement, we won't get the same thing out into the future, which is different than what we saw with exponential smoothing, the simple one. So my last slide here for this video is to talk about Mark Twain also being an advocate of forecasting. And so he has this quote that the past does not repeat itself, but it rhymes. Okay, so the past is a good indicator of the future. There are a lot of similar things. They rhyme, but they're not, perfect. So it's not exact repeating, but it's rhyming.